computer. Okay, so last class, um, as we were running out of time at the end, I gave you a quick final solution to the previous homework. Not necessarily, I don't know, a great um, solution, but actually probably just fine for that one, but not what I had intended. If you remember correctly, um, don't I have another class in here? Then is this not the screen? Do I have another one open? Oh no. Ah, there we go. Just had to reload it. Um, okay, so we had our game master. Our game master took in the secret number. It remembered the secret number, but it remembered it in a singleton. All right, so kind of our design pattern thing we were using. Um, then in the play game function to be compatible with our main, because our main is supposed to look like this, create a random number right here, create a game master passing him the random number, then tell the game master to play the game. Game master remembered the number in a singleton, play game, generated two threads, let each thread know their name, told the threads to go. What did the threads do? The threads went through, they generated a random number, then forever, they made a guess. We printed out what their guess was. We checked their guess against the um, core guess, in the singleton. But this is a function we wrote inside the singleton, check guess. And if you go up and look at that, we see that check guess right here took in a integer guess as well as the name of the person who made that guess. And this is synchronized. So synchronized means that um, only one thread can access at a time. It's something that makes it what's called thread safe. Was there a question online or some rumbling, or was that just a getting muted as I was sitting down thingy? Let's go with that one. Okay, so this was synchronized, making it thread safe. Only one thread can access it at a time. We didn't have to manage it. We just put the word there. Java does all the work for us. All right, what does this guy do? He checks to see if whatever guess was passed in is equivalent to the secret number. If it is, we print out that that person guessed right, and then we kill the program with a system.exit, which kind of gives us a throwback to what we saw in our C++ code when main always returned some number at the end and had an int as the return type. And I just said, that's the way it is. It's because console text only programs historically, because they didn't have like the ability to have pop-ups and things like that in our graphic user interface type things, it had to have some way of reporting back to whoever called it that things went to plan or there was some error or something like that. Um, you've seen kind of the modern day version of that sometimes when you go to a web page and you get like an HTTP error, like a 400 or a 200 or a 305. There's a whole bunch of different numeric HTTP errors that mean different things. You know, site not found, authorization rejected, whatever it is, that kind of stuff. So this would be similar to that, being able to send an error code back out to anyone who might be interested. So this kills the top level thread, which also then kills off the child threads that were running underneath it. Um, return true. Actually, we're never going to get to that line because we've killed off the program right here. We still had to put return true in here because Java expects us to return a Boolean. Um, but in any case, that's what the program currently does. And if we go ahead and run this, we see that we had a whole bunch of guesses back and forth, and in the end, Mike guessed right. The thing is over. So this fulfills the assignment, but let's just spend a few minutes looking at before we move on to the next thing. I want to pivot back to our dungeon crawler, kind of in preparation of moving to Unity here in several weeks. But we want to start incorporating threads into that, maybe having monsters kind of wandering around our dungeon using threads, that kind of stuff. But In any case, if we weren't going to use the let's bail out of what's in here. If we weren't going to use the let's just kill the program and let who dies die approach, and instead we wanted to have a mechanism for communicating between the threads, well, let's go and let's look at the Java thread class and see what's available to us for threads talking to each other. Now, we obviously could have done this with a singleton like we had done in like the previous assignment, where you basically just had something up there where each thread would check, should I die or not? And as soon as they check that and realize, okay, I'm done playing, they bail out. So we could do something along these lines, which is maybe what I would have expected you to do for the assignment. So maybe this guy creates a private Boolean is, well, let's see, game over. We'll set this to false initially. Then maybe we write a function, static, synchronized, Boolean is game over. Actually, it doesn't even need to be synchronized. I'll explain why in a second. Is game over. And this guy would just return the current value of game over. That game over. So this allows our individual threads to ask core, is the game over? Should I keep making guesses or do I need to get out of Dodge? All right. So what we would then do, save this, is each individual thread, maybe before they make a guess, asks if core dot is game over, break. Something like that. So each thread can ask the singleton, is the game over? Which is going to return the value of game over. If it is over, this variable would flip to true. So now what we can do is we can, instead of exiting there, we can say core dot game over is equal to true. So once we have a winner, we set that variable in core to true. The game is over. The next time through, when the thread checks to see if the game is actually over before they make another guess, they see the game was over. And what did they end up doing? Well, because they checked that before they make their next guess, if the game is now over, they'll break out, which is the end of that thread. The thread will then die a natural death. The parent, what do they do after the threads? Well, the parent just sat there and spawned off 2 threads and play game, then ended. So this is kind of like the referee who just said go and then stood to the side. All right, so this is a mechanism by which we could have our individual players bail out of the game. It's called is game over. No, it's core dot game over. Capital O. Oh, did I not make it static? I didn't make it static. So this should be a static variable owned by core that we made it private here just so we are only setting it inside of core. It doesn't need to be accessible outside of core. So only this guy can check it. So pretty similar output. So I probably expected a solution somewhere along those kinds of lines. using our singleton to do something and using that core. Now, just as a let's glance at our thread class real quick for some other options. We're not necessarily going to dive into them at this exact moment because I want to kind of move on past beating this dead horse. But if we just look down here through our threads, let's see here. We have a couple different things. We have join and we have notify. So let's just look at those couple of things. We also have ways of making threads higher priority so they can get additional CPU time if that was of interest to us in certain things. Most of the time, you want your threads to just be managed by Java and they all come out with default thread priority and we move on with life. So here's a couple of options here. So we do have the ability of telling a specific thread to stop whatever they're doing and die. Well, stop whatever they're doing and fall out of their run method effectively. But it does behave as if they were paused. We have another one where we can ask a thread, "Hey, are you still cooking, or have you been told to wait to hold off?" So we could externally pause a thread through interrupt. We could ask a thread, "Hey, are you still cooking, or have you died a natural death?" We do have the ability to have some threads run as something called daemons, which are system level services on a computer that actually hands the job of the thread off to the operating system. Instead of it being run by this program, it's managed by the operating system. And if we did that, if we had our thread running as a daemon, then what would happen is when we did that system.exit, the threads would not have died. The main program would have died, but the main program is no longer the one who was controlling the threads. They were handed off to the operating system. Not what we were doing here. We have this function called join, which we can tell a thread, look, we want to be notified whenever you finish. So join can say, we would put that in an area similar to in our game master. Our game master could do something like this dot join GT1, and then they can similarly do the other thing for join GT2, and that would cause them to wait until those threads were done before this function finished, which might allow us to do some stuff after this if we wanted to. So if you were interested in knowing when a thread finished, or maybe you had a thread, there's a type of sort. Did we talk about merge sort last semester? Oh, God, you guys are going to hate this. We got to do merge sort first before we go back to our, oh, you are going to really hate this. Oh my gosh. So there is a sorting algorithm called merge sort. And what merge sort does is it takes in a list of unsorted values, and then it sorts those values by constantly dividing your list into small pieces and then sorting those little tiny pieces. So it basically divides everything up until you get to a list of one, which by definition is sorted. Then it bounces back up where you have maybe a list of two, and it uses a fairly easy algorithm to sort that little list of two, which then bounce back up and you maybe sort a list of four. And in the end, you have sorted data. Well, the idea there is that could be implemented in a multi-threaded way, where each thread becomes responsible for maybe their initial halves of them. So this thread is responsible for the left half, this thread's responsible for the right half. Then that guy spawns off two threads where this guy's responsible for the left half, this guy's responsible for the right half. Each of those spin off until we get a thread who only has one thing he's responsible for, and then he says, "Hey, he's sorted." Gee, I only had one thing. So something like that, where we're creating multiple threads, and each one of those threads has a task. Well, when a boss thread, let's say, says, He's going to spawn off two kids and say, I want you to handle the left, I want you to handle the right. He then needs to wait for them to finish before he can go and make sure those are sorted. He can't take his next step until his workers have done their part. So he would have to join them. That's where that join function comes in order to wait until his workers have done their part for him to take the next step, because the next step is reliant on their part being finished. Something like that. So that's what a join can be used for. We could also set a maximum amount of time we're willing to wait. So if you want to think about that in real life, if you give if you give whatever, a worker a task in real life, and you expect it to be done within 3 days, and they fall off the face of the earth, maybe you only wait 4 days until you decide, okay, I need to go and check to see was the work done, or I need to assign somebody else to it, something like that. Here's how you can set something to be a daemon. Also set its priority. We've seen this where we tell a thread to just take a nap. We could also tell a thread to basically go to a low priority where they'll yield to other threads. In case we need something to have priority to the processor. All right, so that's kind of the high level thing for threads. And you can use the documentation to kind of mess around with those different things. Generally speaking, you probably wouldn't need to do much more with threads than we've already done, or that we will do with merge sort. Okay. Any questions about stuff up to this point? Go ahead.
I think the assignment we also had to do like the winner is like it's either guess A or guess B. It's not just like you.
Oh, we already did it, didn't we?
No.
Let's see. If I run this guy, I think it says Mike was the winner or Dave was the winner. Yeah, Dave guessed right. Yeah, so I think we fulfilled the assignment. Did we? Go ahead. Well, actually, that's a good question. Why is Dave guessing so many times in a row? The situation for that is, even though Dave guessed right, he is getting CPU time when Mike's last guess was 29, so they are not alternating each other. That should have been managed by this guy being synchronized when we're checking guesses.
Aren't they printing before they do that check
Oh,
guess?
yeah, you're absolutely right. It's not that Dave is guessing extra times. It's that Dave finally got stuff printed to the screen extra times. Because remember, IO is expensive and you kind of have to, you leave the CPU to wait to do your IO. So what we're seeing here is Dave had been waiting for his opportunity to print this, as well as printing this, as well as printing this, as well as printing this. And he finally got the opportunity to print stuff, and he just did a dump of all the things that he had asked to print because it was his turn. So realistically, the way to get rid of this would be probably not have your threads printing each time through. Have core be the one guy who just prints who won, because we really don't have a way of we have no way of controlling how the IO system manages multiple threads asking to print stuff to the screen. What we could have done if we wanted this to be accurate is, instead of having these guys print to the screen, since the game really goes pretty quickly, is we could have just collected the guesses and maybe an array of strings. And then in the end, we could just dump the contents of that array to the screen along with who won. And it would just be that single functioning core, this guy who would do that. So he would say right here, he would print the contents of the array of guesses, then he would say who won. That way our threads wouldn't have to compete for IO because they're not actually spitting out what their guess was each time. Instead, they were just adding themselves to this this list of guesses. Good. You could, but then our software would take longer to run. But you're right. We could tell the threads to take a nap after they do this, and even then, that wouldn't be a guaranteed fix. Um, because you still could have a timing thing. I guess you could randomize the length of time they nap. Some number of milliseconds, maybe, something 50 milliseconds or less, could a random number, and hopefully the randomness makes it pretty unlikely that they both wake up at the same time. Yeah, but certainly. But this definitely points to that problem that IO is expensive. So because we're having our threads display stuff, we're at the mercy of the operating system deciding when they get to put their stuff on the screen. So to your question, the answer is don't have your threads print stuff. That's the real solution. Let's see. Well, one thing we can do here initially is we could take it out of there. And we could do this. And that's even going to be slow for IO. Let me just try this here. So I'm going to move that output for the guess into the synchronized method, which has to run to completion before somebody else gets into this method. So now we'll have this synchronized method spit out to the screen who made the guess and what their guess was, since we have those two values here. And since it's a synchronized, only one thread will have access to this time and this at a time. So we'll print out the guess. We'll check to see if it was a good guess. We'll say we guessed right. And then we can say game is over. And then the threads themselves are checking against whether the game is over. We could actually take it away from threads completely by externally killing off threads. Maybe I'll show that here in a second. But doing it just this way, we know that there's only one thread that has access to this at any point in time. And we don't get to this line until this line is done, which means no other threads are going to be coming in and printing stuff. We don't get to this line until this line is done. So if we run this right now, yeah, exactly. So we still have some mics in here. Let's see who won. Dave won. Yeah, look at all the mics there. Yeah. Wow. We don't even have to go much farther than all the guesses Mike is making. So this is not blocking. This code doesn't block. So we say print something out, it then goes and throws it to the IO system, which then tells us to and then we continue on. So we got to go to the solution I mentioned before. So let's go ahead and write that. So I might say private static string array. Let's call this guy the guesses. For no good reason, I'm making it an array that can hold up to 1,000 guesses. So we are limiting this to 1,000 guesses. We're also going to have a private static int, maybe guess number, start that off at 0. When we get into this check guess, rather than printing something out, what we're going to do is we're going to build this string. And we'll say core dot the guesses at bucket guess number equals that string. So we're not actually displaying it to the screen now. We're capturing it for later display. So we're putting it into this this array. Then we would say guess number plus plus. Now, just to connect this with something else, if you remember the plus plus and minus minus from last semester, and we talked about if the plus plus comes after, the value boils down to its current value, and then we change it. The plus plus comes before, it updates its value, and then boils down to it. And I mentioned that you never have to worry about remembering that stuff if you always put the plus plus thing on a separate line. So in this case, it wouldn't matter if I would have said guess number plus plus or plus plus guess number. The result will be the same because we're not using the value in real time. But this actually would be an example of a time when we could, if we knew how it worked, leverage that and say core dot the guesses guess number plus plus, because this would access bucket guess number and then change it to one greater than it used to be after the fact. So this would work the way we want it to work, but I would still suggest you not write it this way. I would still suggest you update guess number on its own line so you don't have to remember whether it happens before or after. All right, so every single time a guess is made, we will store the information about that guess, not having to compete for IO time. We'll then increase our guess number. We'll ask, was our guess correct? If it was, we'll say who guessed right. Even then, we probably want to be careful with IO. Do we just put that at the end, or do we go ahead and let's check it? So let's say for int I is equal to 0, I is less than actually here. We'll make this work. So we're going to say string temp is equal to that. We are going to then go through all of our guesses. So I is less than core dot guess number. And I would probably call this core dot guess number in here, even though we didn't have to because it is in a static context. But I like being explicit. So start I off at 0, keep going as long as I is less than core dot guess number. I plus plus. And then what I'm going to do is I'm going to build onto this string. We're only going to do a single IO. I'm going to build up a string of everything I want to dump to the screen and then dump it one time to the screen. So I'm going to say temp is equal to temp concatenated with. I'll start off with a carriage return, so it kicks it down a line. Actually, I probably want to put these before that guess. So I'm going to do a core dot the guesses at bucket I concatenated with a carriage return concatenated with whatever temp currently is. Because I don't want it to all be on one line. I want to say, Mike guessed this, Dave guessed this. So what we're adding here is we're saying Mike guessed this, then pressing enter to take us to this line and tacking on our new thing. But then we're going to add on to the next one, add on to the next one, add on to the next one. So actually the last thing we finally have on the very last line will be this who guessed right. And we're going to output all the guesses before that. We actually probably should go through the guesses in reverse to get them in the correct order that the guess was actually made, because the very last guess is the most recent guess. So we would say I is equal to core dot guess number -1. Keep going as long as I is greater than or equal to 0. I minus minus. Then we'll build up this entire temp string where we say, here's our most recent guess, concatenate that with a carriage return. Actually, we probably don't. probably do it this way. I'll start that off as the empty string. We will build that string up with all those things with a guess followed by a carriage return. So it'll be most recent guess, next recent guess, next recent guess. Actually, we should go in the right order, the correct order. As if we're hitting the most recent guess first, and then pressing enter, our guesses will actually be presented backwards than as this code is written. So go back to 0. I is less than guess number. I plus plus. Because then the very last thing that we have will be our most recent guess. When we exit this for loop, temp will have all of our guesses in it, and the very last guess would have put a little carriage return onto the end of it. So then we can say temp is equal to temp concatenated with, put that in parentheses, name guessed right, the actual person who finally won. And then we just do a system.out.println temp. So we're actually only doing one print statement to the screen. If we really, and we probably, just to be protective, go ahead and set the game over to true before we do IO, so that we don't have any sort of race condition between the game is over, but the IO is still stuck in the system. Probably wouldn't notice a difference, since we don't notice that the game has ended behind the scenes, other than the threads have just stopped spinning. Okay, so let's see what this guy looks like. Oh, we're not updating temp here, so we need to say temp is equal to temp plus this. Still got some Daves in a row. Pretty well there for a while. Definitely better. But towards the end, I think I saw several Daves in a row, did I not? Yeah, here's Daves in a row, but oh, I wonder if these got thrown in there at the same time as the guess happened. So to prevent the every now and then one squeezing in, I bet you if we run it sometimes we don't get any repeats. Yeah, so that looks cleaner, but they're probably, if we really wanted to guarantee it, we probably would have to have that core thing that makes them, purposely makes them take turns. I mean, at some point we are killing it, beating a dead horse, but that's a way you can do it. So, I mean, it actually was a good thing we went down this path, because it allowed us to look at, here's a real life example of when that plus plus thing could have saved you one line of code. I still would write it the way I wrote it here. But it also allowed us to really emphasize the idea of how expensive IO is. Even though when I first mentioned IO was expensive, I think I wrote a program that probably printed something 1,000 times. And we saw the difference between counting 1,000 times and printing once, and printing 1,000 times. And we saw how much slower it was because of how expensive IO is. And at that point, when we go and do IO, when we want to print something to the screen, the programmer loses control over the timing, because we've told the operating system, I want this on the screen. Now we're at its mercy, and it's running its own threads to do different things. Go ahead.
Is IO cheaper than it once was?
Well, I mean, I would say no, we probably have better um, uh, better ways of handling it, especially with processors that have multiple cores. So between the operating system spinning off threads and multiple cores, maybe from a time perspective, it's a little bit cheaper. But I almost guarantee most operating systems these days are written to take advantage of performance cores and low performance cores. And IO, I bet, just thrown onto low performance cores all day long. So they're already second class citizens. So the most control a programmer can have is store all the stuff you want to dump to the screen inside of a collection of something. And then just do a single screen dump of all your stuff. And you have pretty good control, let's say. All right. Questions about that? So let's talk about merge sort. And I would prepare to have a bad weekend. And it's not, look, I didn't write merge sort, but we have to learn it.
We get to that the stuff that we were going to do the first semester, you know, the room thing.
Right after merge sort. I thought we were starting it today until I realized we hadn't done merge sort. So if I were guessing, probably next Wednesday or Friday. So we'll build it in Java, then we'll transition over to Unity around week 8. All right. So here's the deal with merge sort. Merge sort is a recursive divide and conquer sorting algorithm that is compatible with multi-threading. I'm not going to have you write it the multi-threading version initially. I'm going to show you how merge sort works. And then I'm going to ask you to write a normal version of merge sort for Monday's homework. So let's look at merge sort example. So multi-threading. So let's give ourselves some numbers. Something like that. All right. So let's assume this is our array of numbers. So maybe we have a int array, AR is equal to new int array, and this has 5 buckets in it. Okay, and then we have filled this up with random numbers between 1 and 10 or whatever. All right, so we filled it up with some random numbers here. Now, what merge sort says is it says, is this array sorted? Now, as human beings, when we look at this, we'd say, oh, it's not sorted. 25173 is not in order. But merge sort doesn't rely on that way of finding out if something is trivially sorted. Instead, what we do is we keep track of start and end. So start points to the beginning of the array. End points to the end of the array. So when we ask the question, is this array sorted? The answer is no. Why? Because start and end are different numbers. So when start and end are different numbers, what do? We divide this in half. Depending on how you implement it, since we have an odd number of things, the left half might be the bigger half, right half might be the smaller half. You could also have it be the other way, depending on how you implement this. Let me give myself some space here. So we'll say start is like that. End is like that. So now what we've done is we make another call to merge sort. So this thing relies on something called recursive calls. I mentioned this is recursion. Recursion is when a function calls itself from within itself, typically with different parameters. And we'll see this by example here. So when we determine that start and end are not the same, we called merge sort again on the first half, however you figure out the first half, where begin and end is here, where begin and end is there, hint, hint. Go back and watch the video when you're doing this. So we've called merge sort here. We've also called merge sort here. Now, since we're writing this initially in a non-multi-threaded way, the call to merge sort on the right half of this thing won't even happen until we've completely dealt with the left half. So let's just go down the line here. So we ask ourselves, so this call to merge sort's currently on hold. It's waiting for its left and right half to get sorted. So we say, is this sorted? Nope, because start and end are different values. So what do? We split this in half. And we get that side, which also is going to have a start and end. We ask ourselves, is this list sorted? Nope, start and end are different values. Call it on the left half, which will be a list of one. Call it on the right half, which will be a list of one. Are those two sorted? Yes. So merge sort will finish for those calls because it's sorted. We're done. Which will bounce us back up to this level where we have to do something called the merge step. So let me steal this and show you the merge step. Happens after we finish dividing and the recursive calls have finished. What hints here with possible variable names you might want to use? Into N2. So now we do this merge step. We create a temporary array that has nothing in it. We're trying to place something in the first bucket of the array. What do we ask? We ask, is the element at begin 1 less than the element at begin 2? In this case, it is. 2 is less than 5. We place the 2. since we placed the 2, we increment begin 1 to be 1 greater than it used to be. And even though it's technically pointing to that place there, right now we have finished with the left half. Why? Because begin 1 has surpassed end 1. So we already then so the next time through, we're going to ask the question, which should come first, an illegal position or a 5? The answer is a 5. So we place that, then we go and update our array. It happened to already been sorted, but we just sorted it, which means when we come back to this screen, it's sorted. This is sorted, which bounces us back up to here. When we do the merge step on here, it's going to sort this 1, 2, 5, doing that same merge step we just did. And keep in mind, we're passing arrays by address. So since we're passing arrays by address, when we make a change in a part of that array, that change is felt permanently in the other parts of the array. Yep, thank you. So 1, 2, 5, like that. Imagine doing the exact same thing on the right-hand side. Bounce back up. This would be a 3 and a 7. Then you'll perform a final merge step on this, ultimately ending up with 1, 2, 3, 5, 7. Your data is sorted. So what I'll do for your homework assignment, I'll give you some starter code that creates the array, fills it up with stuff. I'm also going to find a good like YouTube video that walks through this step by step so that you kind of have something to go off of as you're writing your implementation. But the implementation for Monday will not be multi-threaded. Nothing with threads for Monday. You're just going to write, oh, you're going to hate this worse. Recursion's way worse than threads. So you're going to write this as a recursive application for Monday. All right. I expect this to be a struggle for you. Okay. So some of you may not finish this. It's okay. Throw your heart into it. And once you get to the point where I'm not making any more progress, submit it. You're going to get a good grade. It's fine. You come and see the punchline on Monday. Okay. Questions, comments? Good.
The values are the same.
No, this will work anyways. Yep. For the people online, the question was just asked, does it assume that it's filled up with unique values? It does not. In fact, the best way to test merge sort is to fill it up with 0s and 1s. So you're sorting a bunch of 0s and 1s where you get a bunch of 0s followed by a bunch of 1s. All right, I'll see everybody on Monday. I'll get this assignment up here in the next 20 minutes or so. Let me just make sure I put everything together for you. Take care.